Alright, so now we'll be rationalizing denominators. So rationalizing a denominator, what is that? Well, rationalizing a denominator means writing an equivalent expression without radicals in the denominator. So, taking a look at this problem, this example, I see the square root of 12 in the denominator. That's an irrational number. That's an irrational number. Maybe I can simplify it. So the first thing you try to do is just simplify it, and it does simplify a little bit, because you can write the square root of 12 as the square root of 4 times the square root of 3, and the square root of 4 is the rational number 2. So we get 2 square roots of 3. So I still have an irrational factor in the denominator, but the factor of 2 came out. Oh, I can actually cancel that factor out. I can actually cancel out that factor to make this 1 over the square root of 3. But I still have the same problem, that irrational number in the denominator. So how do I get rid of it? Well, since it's as simplified as it can possibly be, what I'm going to do is I'm going to write an equivalent expression by doing a multiplication of the top and bottom by the same number. So I'm going to multiply the top and bottom by some number. The number that I need is another irrational number that I can multiply by the square root of 3, so that when I multiply the radicands together I get a perfect square. There's a bunch of choices, like I could multiply by the square root of 12, right, and get the square root of 36 on the top and the bottom. I could multiply by the square root of 12, but that's too big. If I wanted to get the square root of 9, I could just multiply by the square root of 3 on the top and the bottom, and that would work. I wouldn't get 36, but I would get the square root of 9 in the denominator. So the goal is to multiply by another square root, another radical. If it's a square root, you multiply by another square root. That's going to give you a radicand that will produce a rational number. In this case, 9 is what I was aiming for. And on top I still have the square root of 3. It doesn't matter that the numerator is going to be irrational now, because all I'm doing is rationalizing the denominator. And now the denominator is the rational number square root of 9, which is just 3. The numerator is still the square root of 3, which is irrational, but the denominator is rational, and that's all we care about right now, because we're being asked to rationalize the denominator. Alright, let's try another one. Rationalize the denominator. Well, let's see here. We can break this thing up first into the cube root of 7 over the cube root of 9. That way I see what the irrational number is in the denominator. The irrational number is the cube root of 9. 9 doesn't have any triplet factors, identical triplets that you can multiply to get 9 that are like counting numbers. So we don't have any counting numbers that we can multiply by themselves 3 times to get 9. Irrational number. And I can't simplify that because the cube root of 9 doesn't have any factors that are perfect cubes that will be rational if I take their cube roots. So what I have to do then is I have to try to multiply the top and bottom by something that's going to make the cube root of 9 into a perfect cube. So I'm going to multiply the top and bottom by some cube root. By some cube root that's going to produce a perfect cube. If I multiply by the cube root of 9, that's not going to work, because 81, the cube root of 81 is not a rational number. The cube root of 81 is not rational. So is there any multiple of 9 that is rational when you take this cube root? Well, let me see. If I multiply the cube root of 9 by the cube root of 3, I get the cube root of 27. That's perfect, because the cube root of 27 is a rational number. So let me see here. So on top I'll get the cube root of 21, which is still irrational, but I don't care. The bottom is the cube root of 27, and because 3 times 3 times 3 is 27, this is the cube root of 21 over 3. A rational number. So there I've rationalized the denominator by multiplying the top and bottom by the cube root of 3. all you have to do is look at multiples of 9 to see when you find a perfect cube. So I was just looking through the list and I said, hey, um, 9 times 1 is not a perfect cube. 9 times 2 is not a perfect cube. 9 times 3 is a perfect cube, 27, because 27 is 3 times 3 times 3. So that's why I use that factorization. Let's try another one. Here we have it, the cube root of 32 over the cube root of 80, and they want me to rationalize the denominator. Before I do that, what I usually do is I just simplify everything to see if I can work with smaller numbers. Alright, on top, I can reduce that to 16 times 2, which is nice. On the bottom, I can reduce that to, what's that, 16 times 5, which is nice also. So let me see, the square root of 16 is just cancelled. That's 4, is just cancelling out. That's 4 is just cancelling. So this is really just the square root of 2 over the square root of 5. If you simplify, a lot of times you get situations where you can work with much smaller numbers. But now I still need to rationalize the denominator, the square root of 5. So I'm trying to think about it. Any multiples of 5 that are perfect squares? 5 times 1 isn't. 5 times 2, 5 times 3, no. 5 times 4, no, none of those. 15, 20, none of those are perfect squares. 5 times 5 though, 5 times 5. So I multiply the top and bottom by the square root of 5, so that the bottom will be the square root of 25, which is a perfect square, nice. So the top will be the square root of 10, while the bottom will be the square root of 25, which is rational, perfect. So it's the square root of 10 over 5, and that would be the final result. So simplify first, it'll give you smaller numbers to work with, but then we still have to deal with rationalizing the denominator. Alright, so here, once again, let's try to simplify first. Okay, let's see. So simplifying first, the numerator is already simplified, I know, because the exponent is smaller than the index, so that one is already simplified. The bottom, on the other hand, I can simplify. So the numerator remains just the cube root of x squared. The bottom, the cube root of 27, I know. And since 4 is bigger than 3, I do have to break that up. There are many ways of breaking it up. When I say many, I mean you could break it up as the cube root of x times the cube root of x cubed, which I think is the most beneficial one. You could break it up as the cube root of x squared times the cube root of x squared, because both of those give you the cube root of x to the fourth when you multiply them. The bottom is out. The top one is the one I want. So I'm going to break that up as the cube root of x to the third times the cube root of x. And then I can still simplify further. Let's see, on top, that can't be simplified. But on the bottom, the cube root of 27 is 3. The cube root of x to the third is x, while the cube root of x is just the cube root of x. So I still need to rationalize the denominator. And the irrational factor is this one. This is the one that still has the radical on it. So I need to get rid of that radical. So I need to figure out what I'm multiplying by. Well, let me see. I need to multiply up to x to the third power. So I can take the cube root of x to the third power. So in order to do that, to multiply up to x to the third power, the factor that I would need to multiply by x, the cube root of x to the first power, to get it to be x to the third power, is the cube root of x squared. So I multiply that by the bottom, and I multiply that by the top. That way, when these two multiply together, we will indeed get the cube root of x to the third. On top, we'll get the cube root of x to the fourth, which we've already simplified. On the bottom, we'll get 3x times the cube root of x to the third. The numerator, we already know what that simplifies to because we already simplified that to x times the cube root of x. So we've already simplified the numerator to x times the cube root of x once. The bottom is 3x, and the cube root of x cubed is just another x, and one of these x's will cancel. So my final result then is the cube root of x over 3x. And that's the final result.